Okay, so now we are going to take a look at the results of this case. Fire up Paraphone, read the data, go to the last time step. Rescale the field. Can you tell me what is inlet and what is outlet? Inlet, outlet. And also, can you tell me why the bottom part of the geometry is completely different color than the top part? You know what this is, right? This is a coolant jacket of an engine block. And you have the bottom part where the cylinders are. And then here in the cylinder head, you have the holes for the valves, etc. What's in between? A gasket. Okay, so there is a gasket with little holes. And if I zoom into the geometry, can you see this? So this is a little hole in the gasket that can show you what is going on here. And also you can see that the mesh is way too coarse or something like this. Now I cut it through the gasket, and if I move it a little bit, I can show you how the actual coolant jacket looks like. Okay, can you please do some post-processing for me? Show me the velocity fields in some cuts. Show me the turbulence kinetic energy. Okay, so here's my candidate for the pretty picture competition. I have the flow coming in, the flow going out. There is a cut here. I have subset the domain on top one of the holes. Okay, and what you can see here is as the jet goes through the hole, you have very high turbulence kinetic energy on the inside. You remember how big the mesh is? Something like 115,000 cells. Now I have to tell you a scary story. This was actually an industrial mesh from 1995, and the mesh was built by hand. And some poor guy spent 3 months of his life building this mesh cell by cell with star CD, and then he resigned and became a dentist. Okay? Which means that mesh generation at this scale is not very easy. I have also created a line of samples that distributes it, but you can see that quite a lot of the flow will go the shortest way from the inlet to the outlet, which means that the cooling is not very well designed, and I guess this is one of the areas where you can see the benefit of CFD. Okay, so for those people who are advanced with OpenFOAM, I now expect you to take this solution, use Scalar Transport foam to do the simulation of residence time by introducing the scalar at the inlet and taking a look at the amount of time that it takes from inlet to outlet. Beware, you have to reduce the time step. You have to initialize the field to 0 everywhere and to 1 at the inlet. You have to set up the convection and temporal discretization schemes for bounded scalars, and you can make me a nice movie by copying this velocity field. For the rest of us, we will now do a code walkthrough because the rest of the day has been for complete beginners, and now we have to get towards the advanced part of the day tomorrow. Do you want to ask me something, or was that just a scratch? Okay, so for that, we will use the solver called Scalar Transport foam. And the tutorial, there is something called the swirl test in the basic tutorials. Okay, I will need to sit down. This will take about an hour, and we will go between the tutorial and the source code to find out who reads what and why. Along the way, you will learn a few things about the structure of OpenFOAM, a little bit about object orientation and C++ programming, and we will break this barrier of understanding every single line of the code. Are you ready? Okay, so Scalar Transport FOAM is a transient solver that will read in the velocity field and the diffusivity field, and it will solve ddt plus convection minus diffusion of a scalar equals 0. Okay? In the simulation that I'm about to show you, the velocity field has been set to look like this. Okay, do you see it? It goes round and round in a circle. And in terms of boundary conditions, I have the inlet boundary on the left-hand side, the outlet boundary on the right-hand side, and then the velocity field that goes around. If I color boundaries with my variable called t, you will see that I have a step profile at the inlet, and at the outlet I have a slightly smeared profile. Okay, so for the experts in the audience, can you tell me what difference in scheme I'm using? Upwind differencing, because it carries a diffusion-like discretization error. The source code lives under solver's basic scalar transport FOAM. And here I have several bits. Okay? First, in the make directory, I have a file called files. Okay? And it says compile scalar transport FOAM.c and put the executable into the location $foam upbin / scalar transport FOAM. Okay, as I will show you tomorrow, when we want to do some coding, we will typically pick out one of the executables, rename it, give it a different name, different location for the executable, etc. Okay? The other things that we have here is something called the options file. Okay? And that one says that apart from the usual things that I need to do to compile this executable, I wish to access the finite volume library, case headers, plus the object files here in the library called finite volume. Okay? Do you remember the beginning of the day? I told you the Lego set, and then in order to write my executable called Scalar Transport FOAM, I will use the parts of the Lego set to reuse the convection, diffusion, discretization, input, output, linear equation solvers, mesh structure, etc., 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 to write as little of this executable as possible. Okay. The business part of the story is the equation that I'm trying to solve. And here's my equation. Do you see it? It says FVM : ddt of t plus FVM : div phi t minus FVM Laplacian dt of t equals 0. You can safely ignore. Now, obviously, that's the equation that I have to solve. But what is this FVM? What is ddt? What is t? Where is the mesh? Where are boundary conditions? Who specifies the start time, end time, etc.? It should all be in these files, but we have to walk through it step by step. Okay, keep in mind that some of the things that I have in here are specific for this executable, and some of the things are used across a lot of executables. For example, reading a computational mesh is exactly the same as it is for scalar transport FOAM in simple FOAM, in the naval hydropack, in radiation calculation, in solid mechanics, etc. and I never wish to repeat the same part of code if I can avoid it. Okay? So let's start looking through this file from the beginning and figure out what is what. Okay, so in the beginning I have a comment, everything that starts with /star and ends with // is a comment, and it is ignored by the compiler in the same way that it is ignored in the input-output part. Okay? Then I have the beginning of the story. This is int main. So when I type scalar transport foam on the executable line, the execution will start here. Okay? And you will notice this #include keyword, which basically tells you that I need to pick up pieces of text file and include them here rather than copy or write them multiple times. Okay? I separate those in two parts. Okay? The ones that appear before main, I will call header files, and the ones that come after main, I will call include files. Unfortunately, they both end up with capital H because the syntax does not allow us to vary this very much. What is the difference between a header file and an include file? Okay? The header file describes the parts of the capabilities that lives in my Lego set, meaning in my OpenFOAM libraries. An include file is a little piece of code that's being used many times. So if I decide to change it, I don't have to edit the code at 500 different places. I only edit that one, and then everybody else includes it when necessary. Okay? As you know, OpenFOAM is written in C++, which is an object-oriented programming language. Who knows C++? Not bad. Okay. The way the language works is it will create objects that need to encapsulate some capability. Okay? We can have a lecture on C++ and object orientation tomorrow. For the moment, I need to tell you something like this. An example of an object is a vector. Okay? It's got three components, x, y, and z. And with vectors, I can do a plus b, magnitude of vector, scalar times vector, dot product of vectors. I can read and write them, etc. Okay? So the things and the definition of a vector that I'm going to have will be in a header file, which tells me how to use this vector. The actual implementation of the functionality of the vector lives together with the header file in a library. Okay? What are other examples of objects on this level? We call them classes. Well, number one, a computational mesh. Okay, is that a nice object? Yeah. You know what the data is, number of points, point locations, faces, cells, boundary patches, etc. What can you ask your mesh? Well, C-check mesh, right? What is your outside bounds? Where is the cell center of cell number 57? What is the volume of cell number 73? And many, many other things as well. Again, the definition of a mesh will be in a header file called fvmesh.h, which will exist somewhere in the library. Okay. Now, how many objects out of the library will I use? Probably tens of thousands. So why don't I have tens of thousands headers here? Because there is what I assume to be a standard set of the things that I need to do CFD, and that lives in a file called fv for finite volume cfd.h. So let's go hunting for one of those. Okay? So what it's got, it's something that I call include protection. Why? Because compilers are very picky. And I can tell to the compiler what is a vector once. But if I tell it twice, it will say, now hang on, how do I know that the first definition is identical to the second definition? And if they're not, which one should I use? Okay, so to help me with that, I have a little if not defined FVCFD, define FVCFD, and then a bunch of include files. So the first time I try and include this file, that's not defined. I include all of these files. If I try and define it again, I say skip over all this. Okay, so what you can see here is a bunch of other header files which explain to me of what's going on, and some of them are interesting. For example, foam time will define an object of class type time. What does that one do? Start time, end time, delta t, write frequency, etc. Remember? Okay. And an object of class time fv mesh will define the mesh. Okay. How many cells, how many boundary patches, what are the volumes, etc. Why doesn't it say vector? Because somebody else pulled it in. For example, FV mesh will have a poly mesh, which will have a point field, which will have a point, and a point is a vector. So in fact, 10 levels below, there is somebody who has already told me what a vector is. And as I told you, there is no need for me to include the same file twice. Okay? So I'll pick the first one, this foam time, and go and look for it. So what does this one say? Again, if not defined, hash defined, blah, blah, blah. And then it's got things like switch, CPU time, clock, first in, first out, stack, time paths, object registry, named enumeration, function object list, etc. Which basically means that my time uses lots and lots of even simpler objects, which use even simpler objects and even simpler objects, etc. Which basically tells you how the library has been built up. First you define scalars, vectors, and tensors, then fields, then more and more complex things, until you come to the level where you can start writing something useful. Okay, so my class time will have a bunch of base classes, more than some other time. It will read something called an IO dictionary control dict. Does this look familiar? Okay, do you remember? I showed you system/control dict, which will have start time, end time, write frequency, etc. And it is obviously read by this piece of code here. Okay. What other things exist in the class? Look at it down here. Root path, case name, path, control dictionary, but also things like write format, write version, write compression, graph format. Does it look familiar? Let's take a look at it. Okay. So here, where's my case? write control, write interval, write format, write compression, exactly the same kind of stuff that I have here. Okay, what other things do we have? We have something called an FV mesh, okay? So here it will tell you that this is a mesh data needed to do finite volume discretization. And then it has got a bunch of things down here that you will be able to recognize, like, for example, cell volume, face area vectors, mesh motion fluxes, cell centers, phase centers, etc. Now, why is the cell center a member function of the finite volume mesh class? For two reasons. The first reason is the parts of the data that belongs to that class, which is points, faces, cells, and boundary, allows me to calculate the cell volumes. Okay? Now, if I ask you for the cell volumes 50 times during a time step, do you want to calculate them again 50 times? No, that would be inefficient. So who should store them? The mesh class. In my case, the finite volume mesh. Okay? Does that have any additional benefit apart from putting some data together? Yes, it does, because if I have a dynamic mesh simulation and my mesh moves, that means that my cell volumes are wrong. But the object mesh that contains cell volumes knows that the mesh has moved. So what will it do? It will recalculate the volumes if you ask it, right? Okay, let's go further down. In this FVCFD, I also have one thing called the argument list. Okay? So this is a very simple class. Which contains the parameters that are needed for me to figure out what I'm running. Executable, root path, global case name, option, additional argument, option found, and various other things. Why is that important? Because in here I am going to have the C-style strings to tell me what I should be running, what options are available, and to figure out the general interface towards the Unix filing system. Okay? Now, if I have an executable with two options, does it matter which option comes first? No. If it does, then the programmer is stupid or lazy. Okay? So who is going to sort them and do all the searching? Well, the arglist class. Okay? So that brings you the idea of what object orientation means. Okay. So what we said now is when I start running the executable, somebody needs to pick up the commands and figure out what I am actually going to be running. The definition of all the objects that I have to be using is in here in FVCFD or inside of the headers that are inside the headers that are inside the headers, etc. of FVCFD. If they're missing, that means that the compiler doesn't know about it and it would complain. Okay, so having finished with the header files, let's take a look at that set root case file. Now please note, the stuff that I showed you so far will have text like, for example, class, arglist, private data, public data, interfaces, etc. Whereas set root case only has a little piece of text. So what does this say? Foam, ::, arg list, args, argc, argv. If not, args check root case, foam, fatal error, exit. Okay? Take a look at my executable and look for argc in argv. And this is the stuff that I got from the operating system. Okay? You remember that fatal error that I showed you? Did it happen to anyone? Yes, it did to you. Why? We tried to run it in the wrong directory, and it says fatal error, cannot find system control dictionary. Okay? Which means that that part of set root case that I have just shown you has failed because it couldn't find the root and the case, meaning the case directory in which we run. So once we are done with set root case, we are going to call a little piece of code called create time. You see what it does now? It says, create me an object of type time called runtime. Use args root path and args case name. What's this args? Well, that's the object of class type arg list that I showed you before. And it will read system and constant, and it will also check whether my arguments has got the option to exclude function object. This piece of code is called a constructor. It will make a new class object called runtime that I can ask questions. Do you have any ideas what runtime actually does? Well, I showed you already. It reads system control dictionary. It finds start time, end time, delta t, various input-output formats, etc. Does it know about the mesh? No. It knows about time. Okay? So now that we have sorted out time, what data do I have available so far in the code? First, I have my argument list, which just helps me interface. Second, I have time. Okay? Which means that the third thing that I have to construct, I have to construct using runtime. Okay? Back to the top level code. After doing create time, I will do create mesh. You see what it does? It says create mesh for time runtime dot time name. How does runtime know what the current time is? Well, it read system control dictionary. It says start from latest time. It read the list of times. It picked the last time and it set the current time to whatever that is. Now I'm going to create myself an object of class type finite volume mesh called mesh out of IO object. What would that be? Input output object. And it will say, read me the default region for this time and you must read it. Okay? What does that mean? Well, if I try and create a mesh out of nothing, how many cells does this have? I don't know. Okay? So there must be a mesh in constant polymesh directory. Did that happen to anyone? Say you take the engine cooling tutorial, there is no mesh, You run simple foam, it says fault foam, fatal error, cannot read constant polymesh points. Okay, why? Because that one says you must read it. Okay, what does this mesh know? It knows how many points, how many faces, how many cells, how many boundary patches, what is the outside bounding box, what is the total volume, what is the maximum non-orthogonality, and all the other things. What can we do with that object? You remember the executable that I asked you to run all the time? Check mesh. Okay, so what check mesh will do is it will create an object of class type mesh, and it will say, please check everything. Okay, and this is the output that you're going to get. You have the idea now? So now that we have done create mesh, I have an object called runtime, which knows the time. I know the mesh, which knows the space. And then I am going to find the next include files called create fields. Okay, now, create mesh lived in the library. Remember? Will create fields live in the library as well? Well, no. Why? Because the fields that are being read by the incompressible pressure velocity solver are different than the fields that are being read by Scalar Transport foam, because, for example, I don't need turbulence here. Okay? So, in my directory Scalar Transport foam, there is a little file called create fields. So what does that one say? It says info reading field T, volume scalar field T, IO object called T, from runtime time name, for my mesh, I must read it, and I will automatically write it. Okay? What's runtime time name? Well, my object of class type time will read system control dictionary, it will point to one time, and now I will go into that directory and look for the object called T. Okay? Also, please notice the consistency. My field in the code is called T. It will be read from a file called T. Later on, I will specify the linear solver tolerances under T, relaxation factor under T, and convection, diffusion, discretization schemes under T. Could I do banana, apple, pear? Yes, I could, but I will go bananas before I wrote 5 of those. Okay, so there's a lot of consistency, like runtime is called runtime, mesh is called mesh, T is called T, U is called U, unless you have a very good reason. Okay? So what does this piece of code do? It will go into the 0 directory, and it will read a file called T. Now, this says the dimension set, mass, length, time, temperature. Above there it will say the field type is T and the object is volume scalar field. Okay? It will have an internal field that will be uniform and 0. But how many entries? Well, it should be the same as the number of cells. So how does this piece of code down here know how many entries there is? Well, there is an object of class type mesh which is responsible for the space, and it will tell you, aha, you have 527 cells, therefore, please make me a field which is uniform with 527 zeros. Okay, what happens next? My mesh has got a boundary field, which is a list of patches. Sorry, has got a boundary mesh, which is a list of patches. And each of those patches has a name. Okay? So when T gets read, it will go into the mesh and say, give me the names of your patches, okay? And I will pick up that name and look into this file until I find the same name, and then I'm going to create a patch type inlet outlet by reading the stuff out of this dictionary. How many entries in that patch? Well, I don't know, but I'll ask the mesh for the patch index and for the size and create the whole field. Happy? Is this easy? You bet it is. Okay? Let's go further. The next field that I need to have is a field U. Okay? That one is a volume vector field. I will read it from the same time and in the name called U on the same mesh, and I must read it. Okay? Now what does that mean? If the field U is not there, kindly fail. Okay? If the field U does not belong to this mesh, it means that the number of entries in the internal field will be different than the number of cells. Okay? If the patches and patch types do not correspond for this mesh, it is going to fail again. Now take a look at this. How many cells in my mesh? 800. How many entries in the U for the internal field? 800. So everything matches, right? Okay. Also notice that I have the dimensions of my volume vector field U, which is meters per second. Do I know this is a velocity? No, not really. It's just a field of vectors that has got one xyz values that happens to have the dimensions of length over time. Okay? So now that I have read my velocity field, the next thing that I need to do is read the diffusivity. Now, is diffusivity a field? Well, it could be, right? If I have a turbulence model, then the turbulence model could give me mu t, which is a non-uniform diffusivity field. But if the field is the same everywhere, why should I store 800 values when one value is enough? Okay? So in my case of scalar transport foam, it is assumed that the diffusivity is constant. Okay? So what I will do is I will open a file called transport properties in runtime.constant. Okay? Why? Because my diffusivity will not change. Okay? That file is of type, creates an object of class type IO dictionary, and I must read it. Got it? When I have read the file, here's my file. Okay, you see, dictionary, transport properties. I will say dimension scalar dt constructor transport properties dot lookup keyword dt. Okay, so what that will do is it will create me an object of type dimension scalar, which has got name, dimension set, and value, and it will put it into something called dt. Okay? Notice the consistency. Dimension scalar dt, lookup dt, keyword dt, name dt. Why? because if I do anything else, I will go crazy. Okay? So at this point of the code, I have the field t, velocity, diffusivity, and then I have a little line here saying hash include create fee. Is that an include file or a header file? It must be an include file, because we said that the header files give me definition of my classes for things like dimension scalar, but they need to appear before I say main. Okay? So this is an include file. Any idea what create fee does? Okay, let's go hunting for it. It will say reading / calculating phase, flux, field, phi. Okay, so phi is basically a dot product of my velocity field and the phase area vector, which is the finite volume way of describing convective transport. It says surface scalar field phi. Previously we had volume scalar field or volume vector field. Volume field has got one value for each cell plus a bunch of values on the boundary, whereas a surface field has got one value for each internal face, okay, and a bunch of values at the boundary. So what it says is read from a field phi from the current time, but now it says read if present. Okay? So if there is a field phi there, you read it. If there isn't, you will make yourself one. Okay? The field is u.sf, where sf is the mesh face area vector. Who knows the face area? Well, the mesh, right? It knows how many faces, where the cell centers are, where the face centers are. It calls the faces and the points, so it can calculate the face area, which means that I can do something like mesh.sf, and this animal here is a surface vector field, meaning one vector for each face, giving the face normal with the magnitude equal to the area. Okay? Now I have a problem. My U was defined on cell centers, and I have 800 cells, and my SF is defined on face centers, and I have 960 face areas. How is that going to work? Well, what I have to do is interpolate from cell centers to faces, U, and then this ampersand is a dot product, saying do a dot product between the velocity and the face area to get my flux. Oh, by the way, if I can read it in, then I don't have to bother with all this. Got it? Everything clear? What do we have so far? Runtime. It knows when to start, when to stop, what the time step size, etc. is. We have a field t, field u, field phi, and a dimension scalar called dt. Okay? Which equation are we solving? Still don't know. Okay? So let's stop with this and go back to the top level code. So here it says calculating scalar transport, and then it does something called hash include current number that I will happily skip this time around. Okay? Then it says while run runtime dot loop. What will that do? It will go start time plus delta t, plus delta t, plus delta t, plus delta t, until the time has reached the end time, and then it will stop. Okay? Inside of every time step, it will do something called hash read simple controls. Okay? So what does read simple control do? It will say dictionary simple mesh dot solution dictionary dot subdict called simple. So what's that? Well, as you have seen, the mesh registered the fields that live with that mesh. Okay? And it will also register the discretization and linear equation settings that live with that. Did you see those files? Yeah, they are system/fv solution. Okay, so we go into the case and we take a look at system/fv solution. And down here I have a subdictionary called simple with number of non-orthogonal characters, which is right here, and some other parameters that are default. Okay. After I've done with that, I say for number of non-orthogonal characters, solve fvm : ddt of t. That will obviously be t min minus t old over delta t in matrix format. Yes, but I can use Euler implicit, Crank-Nicholson, backward differencing, bounded backward. How do I know which one I'm going to use? Okay, so this one knows that it is a DDT scheme for a field called T, which is called T. Okay, and in order to choose the discretization, it will open system/fv schemes. It will look under DDT schemes for an entry which says DDT of t, and it will choose the scheme called Euler. Happy? That will make a discretization matrix. And then I'm going to do the same thing with the convection term. FVM div phi t. What will it do? It say, aha, the name of the field called phi is phi, the name of the field called t is t, and you see how here I have a space? I'm not allowed to have spaces in names. So the name of the scheme that it will use to look things up will be div, open bracket, phi, comma, t, close bracket. Okay? Where will it look? Well, the same place as the last time, which is fv schemes. And down here, under div schemes, it will say, aha, the scheme that I need to have is called Gauss upwind. Again, it will make a matrix. Okay. The third one will have the scheme called FVM Laplacian dt, comma t, where dt is a dimension scalar that had a name dt. Okay, now you got it. Why did I have to have a name? Okay, and that one looks the third bit up here for Laplacian dt plus t. So this is matrix plus matrix minus matrix. Okay, at this level we do massive amount of checking. Okay, so the first thing is, does the matrix refer to the same thing? What happens if I say here div phi k? Okay? Well, I can't solve for t and k simultaneously in a segregated scalar solver, so those two fields need to match. The second thing is, do phi and t belong to the same mesh? If they don't, I could be solving heat conduction in a solid with the fluxes from the fluid. That doesn't make sense. Okay? And the third thing that I check is dimensions. Okay? So, t has got dimensions of Kelvin. d dt is 1 over time, which means that the matrix dimensions are Kelvin over time. Okay? What is the dimensions of the Laplacian dt, comma t? Well, it will be 1 over meter squared, time meter squared over second, time Kelvin, so the whole thing is Kelvin per second. Okay? So if you try and develop a code and write an equation which is not dimensionally correct, the code will find out for you. Okay? And all of this checking happens on all the operations at the matrix and the field level. So in fact, the code looks after silly mistakes that you can find. After that, I say solve. Okay? But which linear equation solver? Where will that look? It will go into system / FV solution. And it will find an entry for the solver that starts with T. It will say the solver that you want to pick up is BCG with this preconditioner, tolerance and relative tolerance is specified, and it will solve for the values. Which values? The values in cell centers. Okay? Once it is finished, it will call a function called correct boundary conditions. Meaning, if I have an inlet boundary condition which is fixed value, there is nothing for me to do. However, if I have an outlet boundary condition which is zero gradient, it wants to say that the values on the faces of the outlet boundary are the same as the values in the cells in front of that outlet boundary. So that will all be nicely correct. What happens in the code then? I call runtime.write. You remember create fields? Of course you don't, right? So let's take a look at create fields. Here it said volume scalar field T is an I/O object called T that belongs into current time. It is registered with the mesh. It must be read and it will be automatically written. Okay? So what the field said is when you make a field T, I am registered with that mesh, and when I say it is the time to write, I will write myself. Okay? Now take a look at the function that I have in the top level code. Runtime.write. What does that do? It says, dear fields, everybody who has registered with me, because I am the database, let me see if it is time to write. Okay? And it will say current time, write frequency, and all the other parameters. And then it will tell all the fields, dear fields, go write yourselves. Okay? And for example, a field called T says I am set to auto-write, and I will write myself where? Runtime.timeName, because the time follows the time steps. Okay? And another field, like for example my transport properties dictionary, which lives in constant, does it have to write itself? No, because it doesn't contain output data, only input data. So everything will be written out, and that carries on until I get to the end of the time loop. Got it? Did you learn something new? Okay, so how about you try and run the swirl test tutorial, and then we are going to have a little play with discretization schemes. Okay, so tutorial lives in basic. Scalar Transport form. It is called swirl test, and it has also got a little velocity initialization tool called setU. Sorry, set swirl.